recording. Yes. So we'll be talking mainly about signals. So I'll say lecture 1. Today is 08/09/2020. Review of Fourier transforms. Fine. So we'll just to brush up our knowledge, we'll review some properties of the Fourier transform before we start. So yesterday I gave a detailed explanation of when you say that you define the Fourier transform GF as yesterday I gave a detailed explanation of what this means. So I won't repeat that because otherwise we'll keep on repeating things and we are anyway short on time. So simply say that we define the Fourier transform of a continuous time signal GT like this, and we can reconstruct GT from this as this, where this GF, I say that the contribution of the frequency or the contribution of the frequency F to the signal GT, right? So now we know that there are certain conditions called the Dirichlet's condition that need to be satisfied, and I'll write those down just for completeness. So in order to have a Fourier transform, of a signal, the conditions that need to be satisfied are: 1, GT so GT should be single valued. 2, GT may, so this may is important, may contain a finite number of finite discontinuities. And 3, GT, so this is a problem. I have to move this to a side. So let's see. GT is absolutely integrated. That is minus infinity to infinity GT dt less than equal to some m, where m is strictly less than infinity. Fine. So this essentially means that if GT is an energy signal, it should have a Fourier transform. Now let's say that we define, so let's define F as the Fourier transform operator to make our life slightly simpler. So f of gt equals gf. This is just a notational practice. Now we know that for real valued signals, we know that for real valued signals, gt equals the complex conjugate of t, or stupidity is this, or gt equals gf e to the power 2 pi ft df complex conjugate. Fine. Equals minus infinity to infinity. I don't need this bracket. df e to the minus j 2 pi ft df to infinity j conjugate of minus f j 2 pi ft df. Fine. Yeah, I can. What I can do is I can open the. Yes, Animesh, I know too much background noise. Sorry, I'm working on this.
So it's manageable. Kindly continue.
Oh, yeah, sorry, but I've kept the chat window open in my phone, so it's in front of me. So you can type there. I should be able to see. So we'll manage. So maybe in a few lectures we'll learn how to do things. Yeah, thanks, Animesh. So this is clear how I work this out. So looking at say what I call, so if I call this thing equation A, and this as equation B,
So what did you write as second and third point?
so see, we know that gt equals g conjugate of t. Fine.
Yeah, I was actually speaking about a bit above, like three properties you gave, right?
Yeah, so these are the not the properties, the Dirichlet's conditions. These you would know from your signals and systems course. That's why I ran through these.
Dirichlet conditions. Okay, sir.
Yeah, yeah. So I don't know whether it's a Ch or a K, Dirichlet's or Dirichlet's. I don't know, honestly. Some people, I've heard people use both. So, well, the only thing is I know is that it's Fourier, not Fourier, because Fourier was apparently a Frenchman, so the R is silent. So GT is this, and so by comparing A and B, you can write, by comparing A and B, you can see that this happens. Yeah, this happens. Now, so we know that for real valued signals, this property holds, and consequently, GF fine, because the magnitude of a complex number and its complex conjugate is the same. So, which means that magnitude of GF is an even function of frequency. And similarly, you can argue that angle of GF equals minus of angle of minus F, which is an odd function of the frequency. Fine. So now I would like you to revise all the other properties of the Fourier transform, that is the linearity property, time shifting, frequency shifting, duality, time frequency scaling, differentiation, integration, multiplication, and convolution. And for the rest of this course, I'll take it for granted that you know all of these. So now we have seen that, or we have seen how do we calculate the Fourier transform of aperiodic signals, and those who attended yesterday's discussion would remember that I had talked about the Fourier, how do we go from the Fourier series, which is for periodic signals, to aperiodic signals, and defined the Fourier transform. But since since we'll mainly deal with Fourier transforms, so or we'll require Fourier transform, and there will be something called, we'll always be dealing with periodic signals. So it's a good idea to define how do we calculate. So the question that I want to ask is there a way to calculate the Fourier transform of periodic signals? Is there a way to calculate the Fourier transform of periodic signals? Can someone tell me?
Sir, we can do the Fourier transform of one period.
Okay, but so for doing the Fourier transform of one period, you will essentially be converting that. So I'll write this again. So for doing the Fourier transform of one period, you will essentially be converting the entire periodic signal into an aperiodic signal, right?
After we have taken the Fourier transform of one period, then we can just repeat it.
So see, you have so now here is the issue. once you have taken the Fourier transform of one period of a periodic signal, you have converted that periodic signal into an aperiodic signal, right?
Yeah.
And the Fourier transform will be once you convert that, you will get a continuous valued Fourier transform,
Yes.
right? But you know that from the duality that see, and the periodic signal has these discrete frequency components, not a continuous Fourier, not a continuous frequency function, right?
Yes.
So if you look at the frequency spectrum of a, so the idea of a frequency spectrum basically comes from the Fourier series that a Fourier series or a periodic signal consists of multiple sinusoids which are periodic, which are whose frequencies are multiples of each other, right?
Yes, sir.
Sir,
So
for a periodic
yes.
signal, can't we just take the coefficients of the Fourier series of that particular signal?
Yes, yes, that's the basic idea. So let's so the that's the basic idea, but there is a slight twist to it. So you might remember this beast. So this is a particularly misbehaved function. I'll try to- Sorry, did someone say something?
Sir, kindly ignore.
Oh, okay. Yeah, happens. So, does anyone remember this misbehaved function?
Yes.
Yeah. Impulse.
The Dirac, yeah, impulse or the Dirac delta. So the Dirac delta function. So you say that delta t equals 0, t not equal to 0, and not defined at t equal to, right? This is a definition such that right, there is no other complication with this function.
Sir, not defined is bit abrupt.
How do you define the Dirac delta function?
Equals to 1, right?
No. It's not equal to 1.
So in like analog, we will be
So the
considering.
limiting case of Dirac delta, you can define the Dirac delta as a limit that
I'm saying the integral equals 1.
yes, the integral. Sorry, yes, the integral equals 1. Sorry, I miswrote that. Such that. So you can define it as a limit, or you can define it as the derivative of the unit step, or yeah, you can define it as the derivative of the unit step, or you can define it as a limit of 1 over n times the gate function. So at t equal to 0, it grows without bound. It's not 1 at t equal to 0, right?
Sir,
So
why don't
see,
we take it as infinity at t equal to 0 instead of not defined?
so when you take it as infinity, the problem is that once you say that okay, this is infinite, the integral, this integral will blow up then.
But it's for a instant, right?
It's for an instant, but then this integral will not be defined. So
you can define it as delta instead of delta, where delta tends to 0. The upper part.
Actually, the definition, one definition is that say I define this function f of delta t. So one of the ways of defining this Dirac, so Dirac delta is a widely misbehaved function. Actually, most of the courses other than signal and systems, we try to avoid it as far as we can. We will try to avoid using it as far as we can, but there are cases when we have to use it. So let's say I define f of delta t as 1 over delta for t equal to minus delta by 2 to delta by 2. You understand this in, right? It can be a closed set or an open set, that won't matter because this is a continuous function. And 0 otherwise. So you see that this f delta of t minus infinity to infinity f delta of t dt is always 1 the area, right? The area under this curve is always 1.
Yes, sir.
And say my drawing is particularly bad, but say for delta equal to, say this is for delta equal to 1, fine. Then for this I say is for delta equal to 2. So this is delta equal to 2, and similarly delta equal to 4. Now this is, so as a limiting case, delta equal to 1, delta equal to half, delta equal to 1 over 4. So as delta tends to 0, I approach the Dirac delta. Fine. So this is one way of defining it. So however, we are not interested in the definitions of Dirac delta. There are infinite ways of defining this function. What we are mainly interested in is what is known as its shifting property. That is, if you have an arbitrary function gt, then gt minus infinity gt delta t dt equals 0. Fine. This property, all of you know, yeah. So,
Yes,
and based on this, we get infinity delta t e to minus j 2 pi ft dt equals so Bhavnik, that I don't know. Between a slight lag. Yes, so that is one problem with these live classes. That when I write on the board, there is some lag. The network Teams network quality tries to. What I'll do is, just a second. I'll try to kill all the other processes except this. So possibly that will improve the network quality and result in a better speed. So yeah, so this thing anyway, this is okay.
Yes, sir.
Jumping for, yeah. So now I have Fourier transform of delta t is 1 and from the duality property, of the Fourier transform, fine. This is okay.
Yes, sir.
Now again, let's invoke the frequency shift property. We get this is my badly written f equals, fine. So this is okay.
Yes, sir.
That I can write the Fourier transform of a complex sinusoid as delta f minus f naught. So consequently, now I know that for an arbitrary periodic signal Pt with a base frequency f naught, satisfying the Dirichlet's conditions for the Fourier series, we can write Pt equals summation k goes from minus infinity to infinity pk k 2 pi k f naught t. Fine. This is the Fourier series expansion of a periodic signal, isn't
Yes,
it?
sir. Yes, sir.
Great. So now I take the Fourier transform of both sides.
Sir,
Yes.
sir,
Yes.
integration of minus infinity to infinity, g of t, delta of t is g of 0, right?
Sorry.
Integration from minus infinity to infinity, g of t into delta of t is g of 0, right?
You're talking about this.
Yes, sir. Yes, sir.
Yes. So what's the problem with this?
Can we say that minus 1 to 1 integration is g of 0?
Yes. You can say that. You can actually derive. So this, I'll. You can actually say that limit delta tending 0 plus, not delta tending 0, delta tending 0 plus, minus delta by 2 to delta by 2 gt This is also true.
Okay, sir. Fine.
Because except at that precise point where the delta function is not defined.
Yeah.
So you cannot just, so this should be 0 plus. That's the only condition here. It should be approaching 0, it should not be 0. So my k tends from minus infinity, k goes from minus infinity to infinity, pk. So this pk, these pk's are constants. These are constant scalars, right? So these remain unaffected by the Fourier transform operation. This. Fine. This is okay? You can type.
Yes, sir.
Animation, everything is clearly visible, only lag is there. Yes. So we'll try to fix that as we move along. Okay, so now I'm just running through the properties of Fourier transform that are important. Fine. So the next thing I would want to do is lecture 1 part 3. The convolution so all of you know why this convolution is important, right? You have done convolution in signal and systems.
Yes, sir.
And you know that if for an LTI system, if we get HT by fitting the system delta T, then HT called impulse. HT is called the impulse response of the system. It has certain properties that I won't discuss. And for an arbitrary xt being fed to the system, yt equals the output. The system output yt equals minus infinity to infinity x tau h t minus tau d tau, and this is also written as this. This you know, right?
Yes, sir.
Now we'll say that so now consider the special case where xt equals e to the power j 2 pi f naught t. We consider this special case, and in this special case yt equals x t minus tau h tau d tau, fine, equals infinity e to the power j 2 pi f naught t minus tau h tau d tau equals e to the power j 2 pi f naught t infinity j 2 pi f naught tau minus h tau d tau, fine, equals so this is xt back, and this is the Fourier transform of h tau of ht, right?
Yes, sir.
So what we see is that if to a linear time invariant system we feed a sinusoid at the input, we'll get a sinusoid at the output. So you feed a complex sinusoid at the input, you get a complex sinusoid at the output, multiplied by a constant. So for a fixed sine, for a simple sinusoid, if you feed it a simple sinusoid, you'll get a scaled version of the same sinusoid, right? Is it clear that if you feed a linear time invariant system a plain sinusoid, you will get out a plain vanilla sinusoid multiplied with some constant, which will depend on the frequency of that sinusoid, right?
Yes, sir.
So this point is very important. So basically, now if you have an arbitrary, and this works for any linear time invariant system. Now, if you say that you have the linear time invariant system in the form of a gate function, you feed it at the gate function, you will get a triangular output. It is in the form of a differentiator. You feed it something, you will get the differentiation. You feed something, you will get the integration. Or you feed it's an integrator, you will get the integration. But the complex sinusoid is one such beast. You feed it to any linear time invariant system, and you will get the complex sinusoid back at the same frequency, multiplied by something. So this is one strange property of linear time invariant systems, or this is one property of linear time invariant systems and complex sinusoids. And we say that because of this property, complex sinusoids are the eigenfunctions of the complex sinusoid. The complex sinusoid is the eigenfunction of the convolution operator. The complex sinusoid is the eigenfunction of the convolution operator. So now I would like to ask you, so you have heard this term you have heard the term eigenvector, right? Why is an eigenvector called an eigenvector? Yes. So the question is, why is an Vishal? So since you have said yes, so why is an eigenvector called an eigenvector? You can use Google actually.
After the transformation, only it gets scaled
Yes.
by a certain value.
Yes. So a vector, any vector basically has two quantities, a magnitude and a direction. Fine. So in terms of an eigenvector, what happens is the magnitude of the vector changes, the direction does not change when you multiply it with a matrix. So even for n-dimensional vectors, you can define its. So you have done 3D geometry in CBSE, right?
Yes, sir.
Yeah. So you can extend that logic of direction. So for a two-dimensional vector, it's easy to define its direction as its slope. In case of three-dimensional vector, you can say that that cos alpha, beta, gamma are the three angles that the vector makes with the three axes. In case of an n-dimensional vector, you can similarly say that the vector makes n such angles with the n axes. So you can say that, okay, the vector is making n angles with the n axis. So basically those n angles describe its direction. So what happens in an n-dimensional case, when you multiply a vector with a matrix, that for an eigenvector, the magnitude of the vector changes, but the direction does not change. Similarly, for an eigenfunction, the form of the function doesn't change, just if its magnitude changes. Fine. So actually, I have developed a MATLAB app that's included in the notes, in the first lecture's notes, that specify what do you mean by. Yes. So there's a video that specifies what do you mean by the eigenvector property, and that in the video I have there's a MATLAB app. You can download that and see what do you mean by the eigenfunction property of vectors and how does it function. So on that note, do you know that we can access MATLAB online? Or everyone from the institute can use an online MATLAB account?
Yes, yes.
So you don't even need a high performing computer for that. You can have anything and you can access MATLAB online. So you can download the MATLAB app that I have developed and try on that. Fine. So this was the third big idea that we would be using throughout this course. The fourth big idea, so right now I'm just jumping through ideas from Fourier transforms and Fourier series. So some things that will be important for the rest of this course, I'm just introducing those. So the next idea that we'll be introducing for this course is bandwidth. So have you heard the term bandwidth? That's the first question. So has anyone come across, have you guys come across the term bandwidth?
Yes, sir.
Yes. Where?
Communications only.
How? Communications, how? This is the first communication course that you are doing.
Extra course.
Extra course?
Like in general, internet, there is a bandwidth limitation. That's why that speed is.
Yes, we'll come to that. We'll come to that definition of the bandwidth. So you are from, I cannot see your name flashing, but you are from EC or electrical?
EC.
EC. So next semester we'll come to that definition of bandwidth. But right now, for our discussion, we'll say that so you know that from the duality property or what you have done earlier in Fourier transforms, that a signal can be or cannot be both limited in time and limited in frequency, right?
Yeah.
Yes. So, okay, we have 2 minutes. Let me try something. So, just since we don't have enough time to discuss bandwidth, let's try. I am trying something else with the microphone. Maybe that will help us eliminate this noise. Yes. So, am I? Minutes. And am I audible? Am I audible now?
The volume of your voice is quite low.
So I can't hear you. Said the voice is too low. The volume is too low.
Yes, someone can speak and
And now it's audible, sir.
yeah, excellent. And now the noise should also have disappeared, right?
Yes.
And let's see. So I'll write the word bandwidth again. So it's visible?
Yes, sir.
Yes, sir.
And there is a
Yes.
slight lag, and this is better, right?
It's negligible. The lag is
Yeah.
negligible.
Yes. So we figured it out.
Yes, sir.
So what I'm doing right now is I'm for the voice call, I'm connecting through my desktop. Meanwhile, my laptop is open and I am using the laptop as I'm using the laptop for I'm using the laptop for writing.
Okay, so tomorrow onwards, we'll follow this model. That I'll use the desktop for connecting the call, and from the laptop, I'll share the screen for writing. So we can, I believe we can stop the recording now and meet tomorrow at the same time.
Yes, sir.
Excellent. So bye. Have a nice day.
Thank you, sir.
All of you.
Thank you, sir.
Yes.
Bye.